All right, let's jump right in. Today, we're going to talk about something kind of mind-blowing. The idea that there might be a single blueprint that can describe, well, just about everything. I mean, it sounds like something straight out of science fiction, right? How could one set of rules possibly work for things as wildly different as the neurons in your brain, a self-driving car, and the entire global economy? Well, believe it or not, there just might be a universal language that ties them all together. Okay, so to really get a handle on the solution, we first have to appreciate the problem itself, which is just the sheer overwhelming complexity of the world we live in. Our world is built on all these systems that are not only super intricate, but also seem to have absolutely nothing in common with each other. Just stop and think about it for a second. You've got the power grid that keeps our lights on. Then you have the billions of neurons firing away inside our own heads. And now these massive AI models that are changing everything. Oh, and also the vast, chaotic economic systems we all depend on. How on earth could you find a common thread in all of that? And that is where this big idea comes into play. The answer to wrangling all this complexity might just be something called abstract systems theory, or ATS for short. And the core idea is that underneath all that chaos, there is a universal blueprint. So what exactly is ATS? Well, you can think of it as a kind of master translator. What's so cool about it is that it's not just some theory for the sake of theory, it's meant to be a bridge, connecting the pure, abstract world of mathematics with the messy, hands-on world of science and engineering. And it does that by hunting for the fundamental rules that all systems have to follow, no matter what they're made of. Okay, that all sounds great, but how does this blueprint actually work? I mean, what makes it tick? Well, it's all built on 4 core principles that give it all its power. So we're going to quickly walk through these 4 ideas. They're really the pillars holding the whole thing up. It starts with defining the basic rules, then focuses on what a system does, uses abstraction to spot hidden patterns, and then lets you build big, complex things from simple little pieces.
First up, axiomatic foundationalism. I know, it sounds super academic, but the idea is actually really simple. Think about it. Before you can play any game, you have to know the rules, right? That's all this is. You start by defining the most basic, unchangeable rules of a system, its axioms. Once you have those, you can start to figure out everything else about it.
Now for the second principle, the behavioral approach. And this one is a really big shift in thinking. Instead of getting bogged down in what a system is made of or how it's wired, this approach says, hey, let's just look at what it does. A system is just the collection of all the possible things it could do over time. So what really matters is the action, not the parts. Third, and this is maybe the most powerful piece of the puzzle, is abstraction. This is the real engine of ATS. Abstraction is what lets you zoom out from the tiny details of one system and see the universal patterns that connect it to a totally different one. It's what makes a single theory useful in tons of different unrelated fields. And the fourth principle is compositionality. Honestly, you can just call this the Lego principle. It's the idea that you can build unbelievably complex things, as long as you start with simple, reliable pieces and have clear rules about how they stick together. It's the ultimate strategy for making complexity manageable. Okay, so those are the 4 pillars of the theory, the rules of the game. But what's the point of a blueprint if you can't actually build anything with it? This is where it gets really, really exciting. Let's look at how these abstract ideas are being used to solve some incredibly concrete, real-world problems. And the applications are huge. I mean, this stuff is shaping entire fields. We're talking about the very foundations of cybernetics, the science of control. It's changing how we design and verify complex systems, making sure things like airplanes are safe before they ever fly. It's even giving us new ways to model really complex, dynamic systems in totally different areas of science. And you even stumble across these wonderfully strange ideas in the research, like cybernetic kittens. And no, it has nothing to do with robot cats. It's actually a powerful metaphor for a system that has its own built-in regulators, kind of like a thermostat for a machine, or even an economy. It's all about building systems that can keep themselves stable, that can basically take care of themselves so they don't spin out of control. And this right here is where ATS gets incredibly practical and can literally save lives. Just look at this comparison. The old way of building something complex was basically expensive guesswork. You build a prototype, you test it until it breaks, and then you try to fix it. It's super costly and can be really dangerous. But the ATS approach, what they call modular verification, is a complete game changer.
It uses abstract models to prove a system is reliable while it's still just a blueprint. It's like finding a flaw in the architect's drawings instead of when the building is already halfway built.
And its reach is just staggering. Seriously, the possibilities here are kind of mind-bending. ATS gives us tools like bond graphs, which is this unified language for modeling how energy flows through any physical system, whether it's a car engine or a human muscle. It's helping neuroscientists figure out the control systems in our own brains, and it's being used to design systems that can actually detect their own faults and isolate them. This isn't just theory, it's a whole new way of seeing the world.
So as we wrap things up here, it all comes back to this one central idea, the incredible power of abstraction. By taking a step back from all the specific details and focusing on the universal rules of how things are structured and how they behave, we can finally start to get a handle on the insane complexity of our world.
You know, there's this quote from the source material that just nails it perfectly. ATS isn't the steel or the concrete of a building, it's the architect's blueprint. It gives you the universal rules of structure you have to follow to make sure that whatever you're building, a piece of software, a circuit, or robot, is going to be sound, stable, and something you can actually control. And that leaves us with one last pretty big question to think about. If we really do have something like a universal blueprint for building complex systems, what's the next incredible thing we're going to build?